All right, I should be recording right now. Just to go quickly over what we're doing in problem number one is we got a 22-foot beam with two supports on each end, one concentrated load of 6,000 pounds, 10 foot from the left support, and a distributed load of 500 pounds per foot for a length of 8 feet at the end of the beam. I was discussing how we basically want this beam to be in what's called equilibrium. Equilibrium means that it's all the forces, the positive forces are counteracted by negative forces, left forces by right forces, down forces by up forces. And then we also have what's called moment forces. Those are forces that tend to want the beam to rotate around it. Now, a lot of these counter forces that we're doing are what we call internal forces inside of the beam. In other words, they're creating forces on the basic fabric, on the material inside the beam so that it counters each other. When you have forces that are, or objects that are in equilibrium and where the forces are applied parallel to each other or coplanar to each other, we basically have three equilibrium equations that we can use. The sigma symbol right here stands for the summation of, the first one is for the moments, those are the rotational forces on it. The summation of forces in the y direction, that's vertical. And then the summation of forces horizontally, left and right onto that. For our assignments, the problems are in feet. When you see a V, that represents shear, and M represents the moment. What's also very important is when you put values into these equations is that you're aware of the convention, the units of what's going to be, whether it's considered a positive force or a negative force. So in our case, we're setting this up this way, where a force going up is considered positive, while a force going down is a negative force. A force to the right is positive, and a force to the left is negative. Now, as far as the rotations, we have a counterclockwise rotation moment, which is considered positive, and a clockwise rotation for the moment is considered negative. So with these three equations, we should solve for the variables that we have in here. Right now, we have two unknown variables. We have A and B. So we're probably going to have to use at least two of these equations, of these linear equations, to resolve the issue. So what I'm going to do is I'm going to go to another problem that's very similar to that one. But as you can tell, I've changed the values somewhat onto there. Now I'm going to zoom out. I've got some of the values in here for the sample equation in here. I'm just using that so I can pull some of the items over easily. So one of the first things that we have to do when we draw this is I've given you the beam diagram located right in here. And one of the first things you need to do is to draw what we call a free body diagram. The free body diagram is basically a line drawing that sort of reflects everything that's happening on the beam, and then also indicates using vectors, these arrows or these moments, where the forces are going to be. So one of the important things about drawing your free body diagram is to first, let's go ahead and bring down our forces onto the free body diagram here. And then what we need to do is we need to, let's go ahead and bring our dimensions over so we can use those. Right there. All right, so the next thing to do is to take a look at the two supports on either end, because they're going to determine what kind of a reaction force you have at each one of these connections. Now, again, in the lectures, we talked about pinned connections and we talked about roller connections. If you look at the support on A, this symbol here represents what we call a pinned connection. A pinned connection means that this beam cannot move either up or down or left and right. That means that that pin, that support, is going to be having reactions which are both vertical, and if there was a horizontal force put on it, you would have a force in the X direction in here. So for the pin connections, I'm going to go ahead and I am going to copy, let's say from in here. I'm going to copy them to my free body diagram. And there we see that the pin connection has a force horizontally of X at the position A, which is the support area. Also has a potential force vertically, okay, which is counteracting the downward forces, Fy, at location A. And that's typically how you would indicate those two. I'm going to shift this over a little bit in here. Now let's take a look at the other connection. Now, this connection right in here designates what's called a roller connection. A roller connection still does not allow vertical movement in here, but it allows horizontal movement slight. That's what these little rollers are indicated. So there will be no horizontal resistance located at this point. The only thing we should have is a vertical resistance. So in my free body diagram, I could take this guy and move it over. Let me copy it over also with our, and I'm going to move this guy up in here. And because it's at location B, I need to change this. So I'm going to go ahead and change this to a B. And I'm going to make this a subscript onto there. So now what we have is, I think we've basically completed our free body diagram located in here. So we have one force, one horizontal force in here to counter any horizontal forces that may be put onto the beam in here. And we have two vertical forces here at the reactions, Fya and Fyb, located right into here. So the first thing that we're going to do is we're going to solve for the horizontal forces. Now we know from our three equilibrium equations that solving for horizontal forces is the summation of all horizontal forces is equal to 0. Well, we know for a fact that there are no horizontal forces put on this beam. In other words, if we were to create our beam diagram here, we would have to show an external horizontal force going onto this beam, which we do not show right in here. So what we're going to do at that point is I can take this guy here, and we can make the assumption, since it is the only force on there, that the horizontal force at A is equal to 0. There are no other forces to counteract it. If you did have a horizontal force coming off from B at this point, or tension force coming out this way, the value of XA would be different. Again, the summation of forces has to be equal to 0. So that's the first part of the equation that we have to do. Most cases, if you don't see an external force in there, you can make the assumption that any reaction force, horizontal force that occurs at a pin connection is going to end up being 0 also onto that. By the way, this is what we call a determinate beam. We have other types of beam which are called indeterminate, where they have too many variables and not enough equations to solve it with that. And for that, we have to use a different method to try to solve that. But for what you guys are learning, this is the simplest way to do it. All right, so we've solved for the horizontal forces. That was the easiest one that we had. Now we need to solve for the vertical forces into here. Once again, the summation of vertical forces has to equal 0. So what are the vertical forces that we have? Which ones are our negative vertical forces? Gabrielle.
I have no idea.
Look at my cursor.
Oh, 9,000.
And
600.
pounds per foot. You have to be careful where you're saying this. Now, how do I know that those are negative forces? They're going down. And if you remember our convention of forces here, our sign conventions, forces going down are considered negative. Forces going up are considered positive. So we have these two negative forces coming down on the beam that are causing stress on the beam. So we have this force here coming down to 600 pounds per foot for a given distance here, so that you have a total force coming in, which is 600 pounds per foot times the 7 feet. And you have the 9,000 pound force coming down. So what other forces are we going to use to counteract those? Well, we have our reaction, our vertical reaction, FYA at support A, and FYB to counter that, located right into there. So hold on one second, guys. So if we take a look at that, what we can do is we can start with our vertical forces dimension. I'm going to go ahead and I'm going to copy this over here. And I'm going to change the values based on what we've got in here. So what we do is the summation of forces has to equal 0. So here's our summation of forces right in here. I'm going to change the values now to match what we've got on the beam, has to equal 0. So the positive, we usually put the positive forces first. So we have FYA positive plus FYB positive minus, in this case, it's 9,000 pounds. So I'm going to change that to 9,000 pounds. And then our distributed load is 600 pounds. And Gabby, I think this is where you ran into a problem with your assignment. You assumed that it was over the entire length of the beam. You had this as 22 feet, correct?
Yeah.
Okay, but that's not how much the load extends. The load, for example, in this example, is only for 7 feet across. So we have to take 600 times 7 is going to be our equivalent concentrated load at that point. Okay, so this number is 600 times 7 feet is equal to 0. Let's go ahead and continue. I can carry this down. I'm going to copy this. And so this number now becomes what? 1,400 pounds? 4,200?
Yes.
And we can get rid of all this other stuff. All right, so let's just do the math, double check. If anybody wants to double check me, please double check me. It's 4,200 pounds, a negative 4,200 pounds. It's coming down, okay? And that is what we call, and I'm going to copy it over. That is what we call our equivalent concentrated load. It doesn't become that important here in this equation, but it will be in the moments because we have to determine where that concentrated load is located along the beam. All right, so let's continue our equation right into here. And what we're going to do at this point, we're going to go ahead and we are going to Let me go ahead and carry it over from here because it's already in the right format. All we've done basically in here is moved it over to the other side of the equation. Now everyone knows how we did that, right? All right, so we had FYA plus FYB minus 9,000 minus 4,200 is equal to 0. We wanted to take these guys and move them to this side of the equation. So we added a positive 4,200 to both sides and a positive 9,000 to both sides. So what ended up happening is these canceled out, and we were left with FYA plus FYB is equal to 9,000 pounds plus 4,200 pounds. I can take that down right to here, and I can say that this is, guys, if I screw up with my math, let me know, okay? 13,200 pounds. Now, everybody following this so far?
Mm-hmm.
Yeah.
Yep.
Just so you know, we can't see your calculator. If you're doing it on the calculator, you could use the AutoCAD calculator maybe, then it'll show on screen.
Okay. All right, so what do we have here? We still have a problem, right? We have two variables, two unknowns. So we don't have an answer for this. So this linear equation by itself is not going to help us. What we need to do is to solve for one of these using one of the other two equilibrium equations. Well, we know we can't do the summation of horizontal forces because we're doing the vertical forces, and we've just used this equation right in here. So we're going to need to use the moment equation to solve the problem. Now, once again, because we're dealing with objects that are in equilibrium, the summation of all the moments, which is the rotational forces, either external or internal, have to equal 0. So first thing we got to do is let's go ahead and let's do a quick little review on how moments are taken. What we have to do is, and I'm going to change these values right in here, but what we have to do is we have to take moments around one of the supports at this point. We're either going to take moments around point A, or we're going to take the moments around point B. So what we're going to do is we're going to take the force moments that are going to accumulate around this point A. So what we're going to do is we're going to take the distance to each one of the loads that's coming down in here that's causing this beam to want to rotate down around this way. Same thing with this distributed load. It wants the beam to rotate this way, which, by the way, is in what direction? It's clockwise. So it's going to be considered a negative moment. The only force we have going up, which wants it to counter that and rotate this way, is our reaction force at the right-hand side. So what we need to do is we need to start calculating the values or the magnitude of these forces times its distance around where you're taking that moment. So imagine if you put your finger right on A and you put a weight on 9,000, it wants to rotate this beam clockwise. If you start pushing up on this support right in here and push it up this way, it wants it to move counterclockwise. So what we're going to do is all of these forces coming down onto it have to be countered by this one, which is the only force going up. Now you have these forces in here, but we're taking the moment right around that point. So where you're taking that moment, you do not take those into effect. That would be 0 at that point because it has no distance. It has no value to it at that point. So let's start with our equation on the moment equations. So we're going to start with FYB. Now the distance here is a little bit different than what we had in the example problem and a little bit different on the problem that you're going to do. that ends up being FYB times its distance from moment A. And I'm going to go ahead and change this so we know exactly that we are doing A. Moments around point A. Right there. That's a positive value. That's the FYB pushing up, which makes it a counterclockwise motion. If we go back to here, our counterclockwise motion is positive. Then we have a 9,000 pound force coming down a distance of 5 feet. Now you guys should be able to interpolate this into problem number 1 without any problem. And then we have another negative force, which in this case is 600 pounds times 7, which is going to be, I think that was, now is that correct? First we got to do the value, correct? The magnitude of the force, correct?
Yes.
So we knew that the magnitude of that force was 4,200 pounds. But this number right in here, the 10 feet, or in this case, we have to evaluate where that equivalent concentrated load is going to end up being from point A. What is the distance from point A to that load, which is going to replace this distributed load as an equivalent concentrated load? So what I'm going to do is I'm going to go ahead and I am going to move this guy. And where do you think it would occur? Anybody?
At the center of that load, right?
At the center of the load. Because it is not a variable load. It is a constant load going all the way across. So if you were to load a beam this way, that equivalent concentrated load is in here. So it's going to be 3.5 feet in there from there. So let's just go ahead. I'm going to mark that right into here. I'm going to do a linear dimension and I'm going to adjust it, okay? Because this needs to be 11 plus 3.5 feet. So this actually needs to be 14.5. So let's do it a different way and then I'll adjust the load. I'm going to go ahead and just draw a guideline for now, right in here. And I am going to move it 13.5. Is that correct? 11 and it's 14.5, right? All right, thank you for correcting me. All right. So I'm going to move that guy right into here. And now I'm going to go ahead and put my dimension there. So that is the location of that equivalent load. I'm just going to copy that. Located right into there. And we know the value of that load was 4,200 pounds, correct? That's the equivalent concentrated load located 14.5 feet from there. So we're going to change this value and change that to 14.5. So all of that needs to equal 0. So we have the one countering force here, and then we have the two negative forces coming down at that location. And with that, we can find our moment value in here, the summation of moments, and we can solve how many variables do we have in this equation? How many unknowns?
One.
We only have one, FYB. So let's go ahead and solve for FYB. So you guys want to help me out here with some of the math?
Sure.
Don't everybody jump. All right. So the first thing that I did was I moved these two values to the other side of the equation to turn them into positive values and isolate FYB. Now this is going to be at 21 feet in this case. And the values here is, what is this value here? 45,000
Yes.
foot-pounds? And can someone do the math for me on that one?
45,000 plus 130,000? 60,900.
60,000,
900.
900 even?
Mm-hmm.
And be careful, it's 60,900, what we call foot-pounds, okay? Because there's a distance value to it and there's a load value to it. So let's go ahead and add these two together. Can someone do that for me? What's my value here?
Added together, it's 105,900.
What was it? 105
105,900.
foot-pounds, correct?
Yep.
Mm-hmm.
All right. And then one last move. Let's isolate FYB. All we have to do is divide both sides by 21. So if someone can divide 105,900 by 21.
5,042.8. We could just round that to 5,043.
5,042.
Yep.
And what was, now let's keep the decimals going. 5042.8.
0.8.
Now notice one thing that happened when I did that. Let me go ahead and isolate this. I got rid of the foot-pounds, right? Because here it was 1,900 foot-pounds, and I divided by 21 feet. So those 2 feet, the denominator and numerator canceled each other out, which left me with a pound force, okay, going into there. So Fy at B, let me go ahead. Is equal 5,042.8 pounds. Everyone got that?
Mm-hmm.
All right, now guess what? Let's go back to our first equation. We just solved for FYB, so now we're only left with one variable, and now we can solve this one without any problems. Let me go ahead, and I'm gonna copy this guy up to here. FYB is equal to that. Now let's go ahead and let's do our, let's calculate. Our reaction forces. Let's copy that back down here. And we can substitute for FYB. Let's substitute 5,042.8 pounds. And solve for FYA. All right, so somebody can please subtract 13,200, subtract 5,042.8 from 13.2.
8,158.
8,000.
158.
You're rounding off, guy.
No, it's actually completely. Wait. Oh, I didn't include the decimal. My bad. Let's see.
What is it?
8,157.2.
Okay, so now we know the value for FYA. Let me go ahead and put the A on here. And I can copy it here. And guess what? We just solved for our reactions. Everyone got it so far?
Mhm. Mhm.
All right, good. All right, so once we have our free body diagram completed and we've calculated for our reaction forces, what we need to do is I want to now create what we call our shear and moment diagrams. And from there, we can establish what is our maximum shear and what is our maximum moment, because that's what we're going to be designing for. We're going to be designing to find out what are the maximum stresses inside the beam, because then it's going to help us. For example, a 2x10 has the ability to hold a certain amount because of its shape and what it's made of, a certain amount of internal stresses. In wood, it depends on whether it's with the grain or against the grain. In steel and in concrete, it's a little bit different. But this is the process that engineers use to be able to analyze beams and determine what the size of the beam is and whether it can span the distances that you're trying to do. So if we have a span of 21 feet, well, let's determine based on the loads that are going to be coming onto it, and that's going to be the next assignment having to do with the codes and tables for applying loads onto them. We need to determine then what is the size of the beam that we're going to do and at what spacing. If you're going to be doing them like joists or rafters, can we do it at? This is also very important so that you don't get way out of hand in terms of money. You want to be able to design it, number one, for safety, but you also want to be economical in your selection of materials. So it's very, very important to do these calculations and to meet all the requirements that you have. So first thing we're going to do is we're going to create a free body diagram. I'm sorry, we just did the free body diagram. Let me go ahead and move this up a little bit. We're going to create a shear diagram based on the information we solved at this point. So first thing we're going to do is let's take a close look at what we've got here. V represents shear. This horizontal line is going to represent where shear is at 0. And then anything that goes up here is considered a positive shear. Anything going down here is called a negative shear. Now shear is usually highest at the supports where you've got this type of supports. Not all the time, but a lot of the times it is. So the way that we draw the shear diagrams is we start from 0, and based on wherever an event occurs, as an example, what I call an event here is our reaction force going up is considered a critical event. The next event that we're going to have is a critical event occurring here, which is our negative force going down at 9,000. Nothing occurs here to change anything in between there. Then we have another event that occurs right here, which is the beginning of our application of our distributed load. Then we have an event here where it ends. And then we have our final event located right here, which is our reaction force going back up. Ideally, if all your numbers are correct, your shear diagram should start at 0 and end at 0 with all your forces. So let's start with the first one. Now, if you notice what I put in here, 1 vertical unit is equal to 1,000 pounds. So the first thing that we want to do is we're going to start at this point. That is our first event going up. I'm going to type in 8.1572. Okay, so that should be our beginning shear going up. So I'm going to go 8.157 2. And that locates me right at that point. Now, remember what I said, that there's nothing happening between this event and that event right into there. But what I am going to do is I am going to go ahead and I am going to draw, unfortunately, let me, I'm going to go ahead and draw the event lines in the same color, unfortunately, but let's go ahead and do that. I can change that. So we have one event occurring here. I'm going to carry it all the way down. And then we have the other events here, which is the beginning and the end. Of our loads, distributed load coming down into here. I'm going to go ahead and change the color of these guys. Just to change them. All right, so from our point where we were, we went up 8157.2. Now we're going to, this is a little bit different than what you did in the example problem next to it. If we take a look at this, why do you think this was going down at an angle throughout the entire length from first support to back support over in here on this shear diagram? Gabrielle?
Because the weight was decreasing.
Absolutely. Because the weight is not decreasing, it's actually increasing, but you reflected. Your answer was perfect, because this is what we call that distributed load. Whenever you have a distributed load, means that the weight around this point is changing as you go. So in other words, if you had 650 pounds, you had 650 pounds for 1 foot, then you have for 2 feet and 3 feet. Overall, in this case, we had 6 feet. So you took 650 pounds times that 6 feet right here, and you know how far down you were coming down with the angle. And once you created that angle, you were good with your distributed load. We're going to do the same thing on our problem in here, but we don't have a distributed load all the way across the beam. We only have it from here to here. So there's only critical events occurring here and here, nothing in between. We are not adding a distributed load anywhere else. So what ends up happening is that we do our shear diagram is shown as a horizontal line right here until we have our next event, which is a negative force, the 9,000 pounds, because it's going in the down direction. And I'm going to go down 9, enter. And then I have nothing again happening until we begin our distributed load at this point. Everyone got that? Yes?
Why did you go down 9?
Pardon?
Why did you go down 9?
Because my load was 9,000 pounds right here. Remember, my reaction is 8,157 pounds going up, right?
Mm-hmm.
So I drew it up. Nothing was occurring on the beam until I got to this 9,000 pound load, right?
Mm-hmm.
So I drew it down 9,000. And there's nothing going on here until I get to this point right here.
Okay.
Now I start applying an additional load at this point, all the way from here to here. So what I need to do is I need to find out my load, which I think we already calculated here at 4,200 pounds, correct?
Mm-hmm.
All right, so what we need to do is we need to sort of copy this guy down. 4.2. Hold on. I can do this a bunch of different ways if you want to. I can also just do a line down here at 4.2 and carry it over to here. Delete this line right in here. And now what I have is I have my start and end point of my diagonal line, because it's a distributed load right there. Everyone understand what I just did?
Mm-hmm.
Okay,
Yes.
If I was to put If I was to put a dimension on here, okay, we know the dimension from here to here is 9. And I know that my linear dimension from here to here is 4,200. That's the distance going up to there. Everyone understand that?
Yes.
If you have questions, now's the time to ask, right? I'm gonna take these guys out of there.
Can you repeat how you made it the angle again?
Okay, all you need to do is to go, you know you're gonna go this horizontally up to this point, correct?
Mm-hmm.
You
Yes.
just needed to find your vertical component.
Mm-hmm.
So the vertical component is from this point, which is the start of the load, to the end of the load was a total of 4,200 pounds. So
Mm-hmm.
this point is 4,200 pounds lower than this point. That gives you
Mm-hmm.
that vertical component. You can just bring it across here and then connect the dots with your diagonal.
Okay.
Alrighty?
Mhm.
Okay. What happens on the beam from this point up to the reaction?
It goes straight.
Nothing, right? So it goes straight across. Now, if my math worked, how far up do I need to go with this?
Well, only up to the 5,042 line on the, where B is.
5,042.8, right?
Mhm.
So I'm going to do a line command. And I'm going to 5.0428. And something went wrong. Nope, perfect. Located right into there. All right, does that make sense?
Yes.
Yep.
All right, now I just got fancy and I wanted to add, I guess, a gradient. To show my shear. All right, so in your problem, it may be different, but in this problem, where is my maximum shear?
Wouldn't it be 8,157?
It's the bigger of the two values. I'm glad you answered, Lorenzo. Now, in the problem that you did, evaluate what was your maximum shear, okay? On problem number 1, that may not be the answer.
Okay.
Let me copy this. Because if this shear ends up being a greater number than this number, this becomes the maximum shear. Okay?
All right.
All right. Okay. Now let's do our moment diagram and let's solve for our maximum moment. And in order to draw, we also got to solve for a couple of other locations. We got to solve for wherever these events come in because the shape of our moment diagram will change based on that. So let's go ahead and let's solve for our maximum moment. By the way, where does our maximum moment occur? Anybody?
It would go at where the 9,000 load is, or where the what's it called? Where like transitions on
Shear is 0.
equals 0.
So it's along this line right into here. That is where your maximum moment is going to occur. So we have to solve for that. And the way we do that is we need to create another, what we call a little mini free body diagram located around this point. We're going to call that point P. Okay? So we're going to locate this right in here, but in our case, it's a little bit different. We have no distributed load, and our load is located how far over? 5 feet?
Mhm.
And what is our load at that point? 9,000? And at what location is P located? It's at one and the same, right?
Yes.
Correct? Hello?
Yeah.
Yeah.
Get this out of here. All right, so we know that vertical load from A is coming down at that point. We know that this is actually located at one and the same. So what we have to do is we have to solve. Let's get this out of the way. All right, so we're going to take our forces in here. We've got one, which is our reaction force, located right here. What was our reaction force at that point? 8157.2. 8,000. 157.2. And it's located a distance from point B going in here. Now this 9,000 pound load is occurring right where we're taking the moment, correct? So we've got a little bit of a problem in here. We actually don't have any moment force being created with that one that's there. The only reaction force that we have is this guy. And it is wanting to move this beam. Our reaction force is pushing up on the beam. Once again, if you put your finger right here on point P, which is represented here, it's 5 feet away from the reaction force that's coming up. Okay, this force coming up, FYA, wants to rotate it clockwise, which is a negative force. We need to counteract it here with a positive rotation to stop it from rotating. Again, we want to be static. So that is what we call the internal stress occurring at that point. So what we need to do now, we need to calculate for the maximum moment, which is located where shear is equal to 0, which is represented by this point right in here. So we know that the summation of all our forces, rotation moment forces around P, have to equal 0 onto that. So once again, we're going to go ahead and take the positive moments. So the first one is the positive moment. Hold on a second. This one's a much simpler equation for us than what we've got in here. We've got our positive moment, this one, which is counterclockwise, and we only have one other force, which is this one going up. And that one happens to be a negative force. So let me go ahead and remove all of this. Okay, and the force is 8.157.2 times the distance it is from point P, which is 5 feet. And so this force right in here, I can take that out, M, which is MP, minus, this is a negative force because it's going clockwise, 8157 times its distance times 5. So since that is the point where V is 0, this will be our M is equal to M max. Can anyone multiply these two for me? Lorenzo?
Oh yeah, I'm multiplying it. Wait. Yeah. Okay. 40,766. No, 40,786. That's with the decimal. It just
40,000.
786.
Point anything?
Nope.
Okay. So it's 40,786 foot-pounds
Yes.
located at that point. So now what we can do is we can calculate what our maximum. I think you rounded off again, but that's okay, right? I guess
No,
we've
'cause
already rounded.
0.2 times 5. It'll.
All right, so what I can do is draw a line in here, and I know I'm going to be going up 4.0786. And that is where my maximum moment is going to be located. Now, there's another event located right in here and another one located right in here. So we need to calculate our moment at this point, and we need to calculate our moment at this point. So let's go ahead, and we're going to need to do a couple of more. They won't be the max because they do not occur at 0. But what we can do is we're going to take our points around this point right in here. So in this case, what we're going to do is we have got our, and this really is irrelevant at this point, the horizontal forces, we really didn't need to do that. Actually, we can leave that in there. We need to now add whatever the distance is for this point to find out what that is. So that distance was 5 and 6, that's 11. I'm gonna go ahead and stretch this out. 6, that's gonna be 11, located right into there. You got one reaction, but now we've got another reaction, correct? We've got this one coming down. So now at this point, we do have to. Is anyone waiting? Sam is waiting. Okay. I think Sam just joined us, a little late, but. All right. So I'm going to go ahead and I'm going to copy the 9,000 force. And I know that is going to be located at 5 feet over. So I'm just going to do an annotate and do it over here. Dimension from here. All right. So now we can take the moments around point, let's call this one point L for whatever reason. All right, so this is no longer going to be the maximum moment, but it is the moments around point L that have to equal 0. So let's go ahead and let's start our reactions to this. Again, we're going from the left to the right, have to match at this point. So first one that we're going to do is our reaction at L. So I guess we could almost call this the moment at L. I should have done that in the other one. This one really should have been moment at P. Okay, so this one's going to be ML. It is not max. All right, so what are our values here? So we've got a reaction force here, which is making it go counterclockwise. And all of these forces here are going to be counteracted with whatever's left over here. Now this is going in this direction. We're assuming that it is counterclockwise, so it's a positive ML, minus our clockwise motion in here, 8157.2, but now the distance has changed to 11 feet. And our distance from here to here, pretend that's 6 feet. All right, so we need to add something to this, correct? What's missing from this equation, guys? I got one force going this way, which is a negative force. Any other forces before we get to this moment? We got the 9,000-pound load coming down, correct?
Mm-hmm.
And which way does it want to rotate the beam around point L? Clockwise or counterclockwise?
Clockwise.
You had a 50-50
No, counterclockwise.
chance there,
Counterclockwise. Because it's more towards the left.
So it's going to be a positive value, correct?
Mm-hmm.
Remember our conventions, our sign conventions. So it's going to be a positive 9,000 pounds, correct?
Yes.
Times, and what's its distance from the rotation point that we're taking the moments from?
6 feet.
Correct. 6 feet. And that's going to equal 0. All right, so let's go ahead and let's do a little bit more math in here, okay? I'm going to move this over, move this down. We're going to adjust this number anyways, so I'm going to delete that for now. Okay, someone do the math here for me, will you? What's 8157.2 times 11?
8157.2 times 11 is 89,729.2.
What was this?
89,729.2.
89,729.2.
Yeah.
And those are foot-pounds, right?
Yes. And 9,000 times 6 is 54,000.
let's bring these guys over to the other side. So what we have then is ML is equal to, it would be a positive 8.9, right? Hold on. And this would be a negative. All right, so what's our value there, guys?
$35,729.2.
What was it?
35,729.2.
Okay, close enough. The numbers when we're rounding off, it's going to vary a little bit, but the whole value of that was 35,7 what?
729.2.
And those are considered foot-pounds. So we know our value then at this point. So I can draw a line. .573. Now I'm rounding off. And then one last point in here, we got to do one more. These should be underneath each other. I know it's going to be a little bit of a pain, but to try to get it fit on the sheet, but just move it over to the right and see if you can somehow get them to fit. Okay, the last one is located right at this point. So what we need to do at this point is find out what our element is going to be at this point, located right in here. So we have to take all of our loads from this side and add the distributed load from that point to that point onto there. So that distance right in here was an additional 7 feet. Located right into there. And I'm just going to call this one K. Okay. And we need to find, what do you think we need to find in here to calculate this for the moment? We have a distributed load. And when we did our first moment equation, do you remember up in here? We needed to find what we had, which was our equivalent concentrated load times its distance onto there. So in this case, that was from the end point. In this case, we're doing it from a point called K. So we need to find out what our equivalent concentrated load is going to be right in here. Now we know the value of the load is 4,200 pounds. But we don't know the location of it. Well, it's going to be half of the distance, okay, from this point to this point. So it's going to be 3.5 feet located over to there for that concentrated load. So we have a concentrated load coming down at this point, which is actually going to be, I'm going to pull this down just a little bit. My mouse is super sensitive here. So I need to make sure that from that point over. This 3.5 feet, correct? Gosh. Okay, so let's do the equation again. This time we need the summation of forces around K. So this will become MK. So let's start from our left. We have our reaction force first. Let's start with that one. And then start working our clockwise and counterclockwise forces from that point. Now, once again, we know that that point is located right in here, which ends up being 18 feet from the edge, from this support. So this force now, the 81572, is not 11 feet away from where we're taking the moments, the summation of moments. It's 18 feet away. This force is now, I think because I changed this value, let's go ahead and delete this in here. All right, so we've got to take this guy. Its distance from K is going to be 13 feet from that location. All right, so that's the concentrated load. And we're taking it from this point right in here. So am I off on that, guys? Let's take a look at that for a second, okay? So we know that this ending of the concentrated load ends up being 11, 7.5. Okay, so it's 18 feet minus 350. That should be 14.5 feet located into there. Okay. For the concentrated load, we know that it is coming in this direction. It's going to be 4,200 pounds. And it is wanting to do what? Go counterclockwise, correct?
Mhm.
So let's go counterclockwise, and it's 4,200 pounds. And its distance from where we are is going to be what, guys? 3.5 feet, right? Okay, can someone do the math on these numbers now?
Uh, 8,157.2 times 18 is 146,829.6.
Okay, now how about the next one? Stays pretty much the same, but we got to change that
Yeah.
value, right?
Yeah.
Because what is the load coming down from here to this point? What is our distance? It's 13 feet, correct?
Yeah.
All right, so this value here needed to change to 13 feet.
And
What is
that's
that value?
107. That's 117,000.
Even?
Yeah.
Okay, and then we got one more that we got to add, which is a positive number. 4,200.
That one is
Yeah, go ahead.
it's 14,700.
14,500.
700.
I'm sorry?
700. 700.
Got it. $14,700. All right, let's move everything to the other side. So we have got these two numbers. Let's add those two. 117 plus 14,700 is how much? These two positive numbers. Actually, it's this one that's going to be positive, correct?
Mhm.
Yeah.
So I'm moving that to the other side, 146, 829.6. $146, 829.6. And then these two, what is the sum of those two?
131,700.
131,700?
Yep.
Okay, and then what's my final number?
15,129.6
pounds. So there's my last point that I need to do. I'm going to go ahead and I'm going to draw a line right here. And that value was 1.513. 1.53. Okay. So we're pretty good right now. Now, you know it needs to get to 0 at this point. And 0 here, your moment is 0 on the support ends where this is maximized out. And because it is a horizontal shear line at this point, this line right in here is a straight diagonal. It's not a curve like what you see with a distributed load where we had a curve located right in here. Okay. So then we had that event. Our maximum moment is located in there. Our next moment was located in here. And our last line, the diagonal like this. Now, the only place we have this distributed load right here is located right at that point. So I'm going to go ahead and delete these lines. I don't need those. And at this point, what I got to draw is probably some kind of a, let's try some kind of a spline line. Located right into there. I should have adjusted that. And that is what our diagram is supposed to look like. Let's go ahead and add a gradient to it. Whoops. Obviously, I did not close that. That should be closed. All right. We know our max is located at this point. And we know our two other points that are located. There's one of them. And there's our last point. Okay. And that is our shear and moment diagrams. And that pretty much is the whole equation. I would just try to move these underneath or put them somewhere where you think they're going to fit onto the sheet. I know it might be asking a little bit too much, but if you can just do something like, that may not even work, but see how you can get it onto the sheet, or create a second sheet if you need to for the calculations. Any questions? Now the last problem, problem 2, is super easy. It's only concentrated loads, right? So you don't have to worry about this. All you got to do is vertical, horizontal, down, horizontal, up, and that's about it. Okay? As far as the moments, you know they're all going to be straight lines. You will not have a parabolic curve or a curve located at that point. What you do have to do, though, is to show me where your moments changes direction. So this will be coming up, go to the next event, then it'll start coming down from the point of maximum of 0 shear will be your maximum moment onto that. All righty?
Okay,
And
thank
that
you.
should conclude our demonstration. Any questions on that as we went through? All you got to do is substitute the numbers for that problem 1 for these values and make sure your math is correct. Okay?
I do have a question though. Like, you guys are recording this, right? Or were recording it?
I am recording it.
Okay, no, just in case I like forget a step or something and I have
I'm
to
going to
like.
try to upload it to, I'm going to find out, I'm going to talk with Mr. Schwartz to see how to upload this video, the Zoom video, to the structural canvas module. You guys can look at it over there, okay?
Okay, all right.
All right.
Thank you.
I am going to stop share, and I got to figure out how to stop recording.